Now let's talk about what's going on with the small numbers. For our examples, we will use 0.00036. So let's see if we could read this. This is our tenths place, hundredths, thousandths, ten thousandths, hundred thousandths, 36 hundred thousandths. And there's our diameter of an electron, 5 femtometers. We know that multiplying by 10 will move our decimal point to the right. So it's actually dividing by 10 that moves our decimal point to the left. So the idea is basically the same, but we just need to make a little adjustment to talk about our decimal point being moved to the left to make a very small number instead of moving the decimal point to the right to make a big number. We still want to pull off those digits that are non-zero, so we're taking the 3 and the 6. Still, we have this rule that we like to keep a number between 1 and 10, so put the point right behind that first digit. We've got 3.6. Now, if that point is between the 3 and the 6, how many places does it have to move? Well, we can see that we've got 1, 2, 3, 4 places we have to move, but to indicate that we're moving to the left, well, for one, if you're saying, couldn't I just make this multiply into a divide and say I'm doing 3.6 divided by 10 to the fourth? I'd say, yes, for sure. Mathematically, that works. But our scientific notation, we're always using a multiply. So the way we indicate the divide is by using a negative exponent. So the negative exponent tells us that we're moving our point to the left, and it's really because we're doing a divide by 10. So if we're using a negative exponent to say we're moving our decimal point to the left, and if our decimal point right now is between the 3 and the 6, how many places are we moving it to the left? So in this problem, 1, 2, 3, 4. In scientific notation, we'll write 3.6 times 10 to the negative 4. And a negative exponent is doing a divide, but we can basically think a negative exponent we're using for small numbers because the negative exponent is telling us move the decimal point to the left. So our next example, the 5 quadrillionth meters, we're going to pull off our non-zero digit, the 5. And where is our decimal point currently? It's right behind the 5. So I'll put my point right here behind the 5. And how many places will it need to move to land all the way out here where it is with this original number? So this is many. 1, 2, 3. I counted it earlier. 15 places. So 5 times 10 to the negative 15 for all these 15 jumps we have to make to the left to get our decimal point from behind the 5 back to its original spot all the way out here. 15 jumps, 5 times 10 to the negative 15th. So now let's talk about going the other way with small numbers. If we start with the number in scientific notation, how do we go back to writing it in that standard notation? Pretty similar to what we were doing with the large numbers. I'll pull off the digits that I see here, the 2.3, just bring down the 2 and the 3, and understand that our point currently, our decimal point is right between the 2 and the 3, but how many places and in which direction are we moving it? 3 places, and it's a negative exponent, so we're moving it to the left to make a small number. We'll move it 1 place over the 2, and just like before, if we have to jump through space, we need to add extra zeros there. So our first jump across the 2, the next 2 jumps are going to be across zeros. It will leave us with 0.0023, or this one is, if this is tenths, hundredths, thousandths, ten thousandths, 23 ten thousandths. Next example, 9 times 10 to the negative 4. So we're going to bring over the 9. We know where the point is currently. It's right behind the 9. And we need to make 4 jumps to the left because we've got a negative exponent, a small number. Our first jump is over the 9, and then 3 more jumps over zeros. So we end up with 9 ten thousandths. Okay, so here's the set of practice problems for you to try. Pause the video, jot these 4 numbers down, write them in scientific notation, and then restart the video. We'll talk about the answers. First example, 36,200. I'm bringing over those non-zero digits, 362. I've got the decimal point right behind the first digit, the 3. And now how many places would it need to move if it's in between the 3 and the 6, and it needs to end up back here behind the last 0. So it's looking like 4 jumps, 3.62 times 10 to the 4th. Next one, 0.0000516. So we're pulling off the non-zero digits 516, decimal point right behind the 5. How many places are we moving it? So a couple things to remember. Number one, we've got a small number. We're moving our decimal point to the left. So this will be a negative exponent. And how many jumps do we need? 1, 2, 3, 4, 5. 5.16 times 10 to the negative 5th. Next one, 80,000. Let's bring over the 8. If the decimal point is right behind the 8, how many jumps do we need? 1, 2, 3, 4. 8 times 10 to the 4th. And the last one, 2 thousandths. Let's bring over the non-zero digit, the 2. We know the point is right behind that 2, so how many jumps and in which direction? Looks like 3 to the left, and we know that's 2 times 10 to the negative 3rd. Now, I mentioned at the beginning of this video that some operations were easier to accomplish with numbers that were in scientific notation. And we won't get too heavily into that just yet. We're just doing an introduction this time, but I did want to give you one quick example. So we have two numbers in scientific notation, 3.25 times 10 to the 5th and 2.4 times 10 to the 7th, and we want to multiply these two together. And a way that we can accomplish this would be that we multiply these number parts, the 3.25 times 2.4, it would equal 7.8. And what we have to think about here is that the only operations we have, aside from these powers of 10, are multiply. So I can multiply in any order. I can multiply the 3.25 times the 2.4, and then I can multiply the 10 to the 5th times 10 to the 7th. And here, this 10 to the 5th is basically 10 times 10 times 10, 5 times. And now we're about to multiply 7 more 10s to it. So we got 10 multiplied 5 times here and 7 times there, for a total of 12 times. So our answer in scientific notation, 7.8 times 10 to the 12th. And if we had these numbers written out with all those extra zeros, it would be, I don't know, just a more uncomfortable problem to have to work through. And as we work with more and more numbers that are large and in scientific notation, we really start to see the value of how easy it is to accomplish many of these operations, really especially multiply and divide.